So good evening, everyone. So our second speaker is Professor Zhang from MIT, and he's going to speak on p-adic heights of arithmetic diagonal circles. Professor Zhang, please.
Thank you. Thank you for the invitation to speak in the conference here, and it's a great pleasure. And hopefully there will be opportunity to be the location in person in the future. So my talk will be about a p-adic version of gross Zagier formula for high dimensional Shimura variety. So let me let me start by maybe recall very quickly.
So
yes.
Yeah, can you please remove your video from that is available upstairs? Okay. So.
Oh, okay. How do I do that? Actually, let me see.
Sorry.
Oh, from here. No. Oh, because I'm sure. Oh, maybe I should just stop the video here. Sorry. What's going on here? Oh, I'm not so sure what happened actually. No, it doesn't work.
Just drag it, that will work.
Okay, right. So, yeah, actually, it's been a while.
Perfect.
Maybe to the left corner.
Yeah, okay.
Wait. Still there, right? Still.
Just drag it out. They're saying. Yeah, perfect.
Okay. So that's a good trick. Thank you. So yeah, let me recall. So the gross Zagier for Shimura curve, and it's p-adic version. So let's fix. So for this talk, we will fix. Say F is a totally real field. So and F prime, a quadratic extension, CM extension. So we work with so those will be fixed. So for gross Zagier, so I have a Shimura curve. Let's say I fix a quaternion algebra over F, such that my quadratic field can be embedded. So I can consider Shimura curve. So Shimura curve. For suitable level, Shimura curve. So X. Suppose I have a abelian variety parametrized by the Shimura curve. So this means it appears as an isogenious factor of the Jacobian variety of the Shimura curve. So in this case, so I'm going to fix this map. Well, actually the map can be varied, so you can change the map. So then I have CM points attached to my given quadratic extension. So I get the so-called generalization of Higner points to Shimura curve. So in this case, so if I take if I consider this point, so I get a point defined over certain abelian extension of F prime. So I have some point, let's call it P. Well, let's say P. So same points. So let's say I have a point P attached to F prime, defined over some abelian extension of F prime. Then I take the trace. So maybe actually let me just write the point as the point defined over F prime by taking trace. So then the gross Zagier says generalization with Zagier were due to Xinyi Yuan, Shou Zhang, and myself. So we computed the heights, the rotated height. So the rotated height will be equal to the derivative of the Hasse L function attached to A, which is the same as the L function attached to certain modular, auto modular form attached to A, or automorphic representations of GO2 attached to A. So the derivative at the central point. So here, let me see, it's 1. So 1 is here, the central point. So again, it's meant to be just as an example. So here, I'm ignoring some other important factors. Okay. So there's also a p-adic version where so parent real and more recently Daniel Dizzini, where one computes the p-adic height pair, at least in the ordinary case. So the p-adic height pair when all the places above p are ordinary. Okay, there was also Kobayashi's work in a super singular case, at least in the case when the base field is rational number. So in that case, you compute the p-adic height. So it's p-adic height. Okay. So that's what happened in this classical situation of GO2 or inner form of GO2. So attached to you get a Shimura curve and some divisors where you relate the height or p-adic height to the derivative of the L function or the p-adic L function, suitable p-adic L function. Okay, so now let me the goal of this talk is to consider so the high dimensional generalization here. So let me recall that. So the setting of so-called Gangross Prasad. Gangross Prasad.
Before you go on, could you say a little about how this identity is related to gross Zagier in the classical sense?
This identity. Actually, the identity I wrote here is good question. So thanks. So in the classical gross Zagier really. So let me use a different comment. So gross Zagier consider x mod of n. So then you have a imaginary quadratic field. So then you have then if you consider a new form, let's say new modular form level n. So you consider the attached Abelian variety by Ekar Shimura, and so then you can favor of complex multiplication give you the Hegelian points. So here you have the Hegelian points. So this is okay. So here's more general in the sense. So gross Zagier, remember, gross Zagier requires a so-called Hegelian hypothesis. So you impose a condition on this quadratic field, and I think the condition is roughly so the factor of all the factor of n. So the level n, all the factor of n must be split in the quadratic extension. That's roughly. So here somehow we're able to remove all those sort of conditions while also considering total real field. So in some sense, the maximal generality for the GO2 case. So in this case you get that's the gross Zagier considered, and also what the parent real considered in p-adic.
So when we talk about gross Zagier results, I usually think of the factorization or the p-adic valuation of some of these modular forms, but so identities like this are an important step in some proofs, are you saying?
Oh, I'm not sure. So the valuation of here, so here actually this identity here it's actually real value, right?
Yes.
So actually I don't have. So can you see your question again? So the real number I cannot consider valuation, or maybe you talk about the p-adic for Zagier. The p-adic one, you have a p-adic height with a value in some p-adic number. Yeah.
Maybe it's maybe there's more than one formula that goes by the name of Zagier, but I just think of it giving a factorization.
Okay. Okay, so maybe that's relevant to the work of Waldipurge. So it's actually coming up later. So maybe we can at that point we can discuss again. Yeah.
Sure.
Yeah. Yeah, it's true that many different versions of Zagier. You know. So here I'm talking about the height parent and or the p-adic height parent. Okay. So let me continue with the Gangrosprasad formulation. So here, so here I'm looking at. So very sort of overview. Overview. So we will be considering a situation like the following. So I still have my quadratic extension being fixed. So we use the same notation. So we consider, well, in general, you look at a reductive group G and a subgroup H. So the example above, I will have what I had was GO2 or some quaternion algebra, B cross, where H will be the torus attached to the quadratic extension. So the restriction scalar of a multiplicative group. So that was the example we had above. So then we'll be considering so there are two settings, two parallel settings. One is I can consider automorphic forms on the group G, and considering, so I can consider automorphic form as pi is automorphic representation. So it has to be the automorphic representation of G, or maybe G of Adels. So here, let me again put a new notation here. A is Adels. The room of Adels of F. So maybe, yeah. So then I can consider a function, or vector in pi. So we can consider phi integrate over H. So here, let's see the notation here again. So here, so the bracket H indicate the identity point of H, quotient by the F points. F is my global field. So I can look at this integral, and this is often related to L functions. So this will have a factorization. So this integral, or maybe actually more precisely, in all the example I will consider today, it will be really the square, absolute value square, which matters. So this will be decomposed. So as a, there's L factor, so attached to pi, suitable L function. Okay, and now I'm using automorphic normalization where the center is actually half of one half rather than above. I was using 1 as the central point for the L function of a binary variety. So here it's half, which plays the central point. So then, but there's also local factor. So actually, let me move a little. So So this is, you can view this as a factorization of an integral into some global factor, which is the special value of L something. But also there's some important local factor where, so we write as alpha v, 5v maybe 5v. So just to double in this, because I'm taking square. So this is sort of the formulation of Waldipurge and Ichino Ikeda. So Waldipurge did this in the GO2 case, or inner form of GO2. So Ichino Ikeda made this formulation for the gross Prasad situation. So here, I mean, this is really not a precise conjecture because I did not tell you what will be what will be the group G and H. So in general, this might not be true. So, so it's really a kind of a template. So template to, so let me emphasize here. So this one, this sort of, well, this identity. So this identity is expected to be true in many, for many pairs of G and H. So the GGP or the Gangross Prasad case. So which is what I want to focus today, is the following group of G and H. So here, so let's consider let's say GGP pair, H inside of G. So this is the following situation. So let's fix one Hermitian space. It's called Wn. So this is a Hermitian space. So it's a vector space over F prime of dimension n. So together with the Hermitian form, then let's consider a subspace of codimension 1. So Wn minus 1. Okay, let me just, so let me write W and W flat. So this is a codimension 1. So codimension 1, non-degenerate Hermitian space. So from this embedding, I can form an embedding of a unitary group. So let me write a U of W flat. So U of W, both are unitary group. So that's the group I consider, but actually this is not exactly H and G. In fact, the embedding H inside of G is the graph of this embedding. So we consider G to be really the product, where H is the smaller unitary group. So embed diagonally, so the diagonal embedding. So this is the sort of the key situation we want to focus in this talk. All right, so this is the one I want to focus. So as you can see that this is relevant. I mean, this is related to the Rankin-Selberg. So the remark is that so if the quadratic extension is split, well, we didn't really allow F prime to be a trivial extension. If this is split, then unitary group will be isomorphic to general linear group. So in this case, this is really sort of, this is the Rankin-Selberg pair, GON minus 1 embedded into GON times GON minus 1. So which is well known to produce, or if you look at this integral, it will produce the Rankin-Selberg integral. So in some sense, the unitary Gangross-Prasad pair is a twist of the Rankin-Selberg pair, but it's an outer twist. So unitary group is an outer form. There are outer forms of GON. This is the Rankin-Selberg. As generalized by Zagier, Piatetsky, Shapiro, and Jalaika to higher rank GON. Okay, so in that case, so I have this factorization. So in that case, indeed, so Ichino Ikeda gave a recipe. So Waldipurge actually did the same for GO2, where what exactly this local factor is. So it's some integration. So in this case, so this local factor, so alpha v, v really can take two different vectors. Maybe it's lies in pi v prime lies in the contra gradient, so the dual representation. So in this case, so this has a very explicit formula given by the integration of matrix coefficients. I have pi v over h. So this is the tautological parent between pi v and pi v dual. Or if you take a unitary representation pi v, then you can take the inner product, invariant inner product. Then you take the integral. So this is the Ichino Ikeda canonical local invariant linear form. So the role it plays is that this has a very good invariancy property. So this is linear functional, and pi v tends to pi v dual to a complex number which is bi-invariant. It's invariant under both factors. So it's h times h. So it's invariant. So it's a canonical construction when you take double, when you double this sort of space of when you pair pi and pi v dual together. Okay, so that's what happened. This identity is actually proved in the case of a unitary group. So it's known in the unitary case. So it's known for unitary group. For unitary GGP triple. So pair. This pair I just introduced. So there's also conjecture for orthogonal group. So you can just replace formation by quadratic space. In that case, the corresponding conjecture is still unknown and not proved. So this is due to the work of many people following Zagier and Rallis. So Zagier Rallis proposed a strategy of proving this identity. So in the case of GO2, this was done by Waldipurge like 30 years ago. So maybe almost 40 years ago. So, okay, so that is the Ichino Ikeda formulation of Gangrus-Prasad conjecture. So so this is about the central value. So we get a central value of L function. So now to go back to Zagier, so one version, one generalization of Zagier to high dimension is to consider well, as you can guess, so the Zagier case was related to Shimura curve attached to inner form of GO2, and also you have Hegel divisors attached to this torus, attached to this quadratic extension. So here, one generalization to high dimension would be consider Shimura varieties attached to so-called GGP pair, at least, well, let's say in the unitary case. So, well, to have Shimura variety here, I have to impose. So this identity was pretty general. It does not have any restriction on the formation space. So rather, okay, well, to have Shimura variety, I have to impose a condition on Archimedean place. So now let's see the next part. So we consider Shimura unitary Shimura variety. So here I have to impose a condition that So the condition imposes that this Hermitian form, Hermitian space, so W and W flat, so both have a signature at Archimedean place. So remember, my f prime over f is CM quadratic extension. So for each Archimedean place, locally I get a C over R, right? So I get a Hermitian space over C over a complex number. So I want the signature to be n-1 at one place, exactly one Archimedean place, and then definite at all other places. So the signature will be 1, 0, 1, n0, n0, and so on for the Archimedean place, except at one distinguished Archimedean place, which is n-1, 1. And similarly for the codimension 1 subspace. So same thing here. -2, and so on. Then it's definite at all other places. So then there will be a natural choice of Shimura data, and you get a Shimura variety. So Shimura variety attached to G. Okay, let me write as Shimura G. Parameterized by compact open subgroup of the finite adenic point. So this per system of varieties, and also the embedding, the induced embedding also give rise to a embedding of families of subvarieties. So recall G is actually the product, so the dimension of the Shimura variety. So okay, and also the reflex field. So the reflex field is actually f prime. Well, I didn't really tell you the Shimura data, but in this case, there's essentially only one way to do it. So you get a reflex field in its quadratic extension. So I have this embedding of varieties over f prime. Okay, perhaps when n equal to 2, the reflex field might actually be smaller, but anyway, so let me just pretend everything is over f prime, this quadratic extension. So the dimension over spec f prime is respectively, so since this is a product, it's n-1 plus n-2, and the smaller one has n dimension or 2 dimension, n-2, yeah. Right. Okay. So now we can try to plug into the the formalism of a Zagier formula, right? So I mean, I have a subvariety, so maybe I should compute its height parent, like the rotated height. So in that case, so that's essentially the Zagier essentially corresponding to the case when n equal to 2. Zagier essentially the case equal to 2, where you have some 0-dimensional Shimura subvariety, which are sort of CM points on the Shimura curve attached to G. So you have in that case you have a divisor. So okay, so now let me actually I have to discuss a little bit height parent. So here I have abstractly have a situation where I have a variety. Let's pretend it's it's projective. I mean, in general, I might have to compactify, but let's say I have well, actually, it is projective already if the field is not equal to Q, because of those those positive definite places for the Hermitian parent. So I have a smooth projective variety over some field. Well, let's call it F, although okay, it's F prime actually. Suppose I have then I have a Chow group of Chow group. I can also consider codimension I. Let's see. So there is a cycle class map. Let's say to the complex points. Well, let's say I have embedding into C of So here I have a Q vector space, and then I consider the cycle class map to some cohomology theory, so some V cohomology. Okay, let's just say I have V cohomology theory for the geometric fiber of X. So I look at the kernel of the cycle class map. So I look at this cohomological trivial cycle. Kernel code. This is the kernel. So the cycle class map. So then, I mean, conjecturally, there is a parent. So the Benhenson Block. So I made a conjectural definition. So generalizing the Tate height parent. So this height parent. So this height parent exists when the co-dimension is the dimension of X plus 1. So really what happened is you take some integral model, so that the total dimension of the integral model is the dimension of the generic fiber, this variety, plus 1. So in that case, you have a really complementary dimension. You have two cycles in complementary dimension. So you expect to take some arithmetic intersection parent. So this height parent, I mean, unfortunately, this height parent is not a completely defined unless you impose conditions such as if the variety has good reduction everywhere, or a very strong conjecture on the special fiber of. I mean, first of all, you have to assume X has a regular integral model. Then you have to assume the special fiber has satisfies very strong conditions on. Satisfy the conjecture of Tate and so on. So it's hard to verify in general, and also even if the parent is defined, it is relatively hard to. Maybe it's not even. It's hard to verify it has nice property relative to correspondences. Recalling in our case, it's important to consider the height parent between cycles, but also we have Shimura variety. So the Shimura varieties we have come with a large supply of correspondences. So corresponding to the Heck operators, so Heck correspondences. So for example, one thing you want to have is that the Heck correspondence. The action of Heck correspondence on the cycles, on the child group, should really depend only on its action, the induced action on the cohomology. At least when you plug into the height parent. So in other words, if you have a correspondence, Heck correspondence, if it acts trivially, namely if it acts as 0 map on the cohomology of the Shimura variety, then it should induce a 0 map on the child group of a trivial cycle, a cohomology trivial cycle. That is a very strong, it's a consequence of a conjecture of Benhenson Block on algebra cycles over a number of fields, but it's impossible to prove, right, unconditionally. So because of that reason, you want such property, right? You want such property because, basically you want the child group. In the case of a Shimura variety, you hope this is, as a Heck module, you want this to be automorphic. Which is known in the case of Shimura curve. So there's no. That's why in the case of Shimura curve, in our work with Xin and Shou, we had a lot of flexibility to change Heck correspondence. I can use different representative of Heck operators which have the same induced action on the cohomology. they all have the same action on the child group, at least on the on the degree 0 divisor on Shimura curve. So that gives you a lot of flexibility, where this flexibility is nearly impossible to verify in high dimensional case. Okay, so that's one reason it's actually beneficial to consider the p-adic height. So here there's height pairing defined by Nekovar. So Nekovar has defined a p-adic height. P-adic height pairing, which still requires some work to to define. You have to verify, for example, the width monodromy conjectures for the special fiber for some suitable integral model. You don't need an integral model to formulate width monodromy, but in practice you have to study some integral model to prove with monodromy. But anyway, it's much easier. It's relatively easier than the Benhenson Block height, which are real valued. So here there's a p-adic height valued height pairing. So it's the same thing, but with the value in QP. So notice here. So my the domain of definition is actually Q vector space, where the target here is a either real number or p-adic number. And also this requires some additional choice, some Hodge splitting. So it's less sort of, it requires a choice to make this definition, unlike the Benhenson Block height. But anyway, so that's okay. You can make some. You have, in other words, you have not just one p-adic height. You have a family. Okay, so if you plug in this sort of, if you apply the p-adic height, so this has nice property in the sense the correspondences behave very well. So in fact, this height pairing, the p-adic height pairing, really factor through the cycle class map. So the p-adic Abel Jacobi map. So there's a map to the Seymour group, the Bloch-Kato Seymour group. So let's say the p-adic. So this is the p-adic cohomology. Twisted by I, so make a theta twist. Same definition. H1. J minus 1. Okay. So really, so it's actually, it's a parent between the Seymour group. So this is the so therefore, the correspondence will behave very well because
Excuse me.
Yes.
For the choice of P, do you have some condition like ordinary assumption?
I think Nekovar's definition doesn't. For the defining the height pairing, you can choose any split to make this definition, right? So at this stage, you don't have to impose any ordinarity condition. Mm-hmm. But that's a good question for the next next part of the talk. I have to impose ordinarity because of this, the p-adic L function issue. So this behaves well. So well behave relative to with respect to correspondence. So just because it's factored through this pairing between the Bloch-Kato Seymour group, which depends on the cohomology, only on the cohomology. So, so it's easy in some senses. It's easier to deal with. Okay, so then I can now go back to my. So here I would discuss, abstractly any variety, height pairing and p-adic height pairing. So going back to the Shimura variety situation, so I have, so go back over here, I have Shimura variety attached to permission spaces. So now I have to make a following, so to speak, the working hypothesis. So here we care about the cohomology of Shimura variety. So the working hypothesis I want to make is that we want to have a good understanding of the cohomology of the Shimura. So let's say cohomology of the Shimura variety. So the état cohomology for G over the algebra closure. Well, okay, the p-adic cohomology. Let's see, p-adic état cohomology. Okay, here I'm fixing prime P from now on. So this should decompose as expected. So in a sense, it should be a sum over. So okay, this has two group actions. One is the Galois group, the absolute Galois group of F prime. Other one is the non-Archimedean point of G. So when I expect this decompose at least modular, some sort of less important term, should be a sum over automorphic representation pi, or the finite part. Okay, tensor. Let's see. I should have switched them. Switch the. Okay, let me switch here. So, so I have pi tensor, the Galois representation attached to pi, to the p-adic Galois representation. Okay, here I'm kind of identifying QP bar with complex number in order to identify, in order to view automorphic representation to be a representation over QP bar. So here pi is say cohomological automorphic representation. So showing up in the cohomology. So here, let's say I will only consider the middle degree. So in fact, I'll only consider those pi which are so-called, tempered. So they're kind of the nicest. Let's see. So in the case of pi f, pi, so tempered, or so to speak, generic tempered cuspidal. Let's say stable in a sense is space change. Space change to GON from unitary group to GON. The base change remains cuspidal. So in that case, when you expect rho pi to be a irreducible n-dimensional Galois representation. Well, actually, sorry, I should have used unitary group. G is unitary group. So U of W. So then when I take the product, you really have two factors. So this is okay. This might not be known in this generality, but at least if you impose some conditions, local conditions, you do have such decomposition of cohomology of Shimura variety. So we assume this. So from here, I so if I consider the Samuel group of so from here, right? So I get a decomposition. So I can decompose. So if you look at certain degree, H1 prime of certain degree of the cohomology. Although the degree we care is either middle one, so which is okay, I cannot remember the degree. Anyway, it's the middle degree. Okay. The middle degree. Make some theta twist. So this will be okay up to let's say ignore the less important term. So I get this automorphic representation which has no Galois action, so it does not really participate taking cohomology. So then twist by H1 of the Seymour group. Sorry. So you impose the Bloch-Kato condition. Sorry. Yeah. Sorry, here. The rho pi. So here, let me just say that, okay, here, again, there's some theta twist involved. So the effect of the theta twist is to make sure that the ending, the output is a weight -1, Galar, I mean, motive, whatever. So, so here, this decomposition. So now if I have, I mean, remember I have a sub-variety of correct dimension. So the class, so applying, so okay, let's say if I take one linear functional, say if I do inside the dual representation, so the contra gradient representation, then I can apply the linear functional. So apply linear functional here. So I get an element, I mean, I get a map to the Seymour group, right? So therefore, if I input, let me move it a little bit here. So if I input the class, remember I have a class defined by my sub-Shimura variety. So if I apply this class, if I apply this composition with this map, so you start from here, you apply this map, so you get a class. I will denote as an integral. So the integral sign has no meaning. It's just a notation for this class. So this is a notation for the image. So this is by definition is this projection of this class to this. First you project down to the pi component, then you make you use this mark linear functional to send it to the Seymour group attached to pi. So that is my sort of this. So we should compare this class here. So with the integral, which appears in this identity here. So I intentionally write it as if it's the same as it's analog. It's meant to be analog of this integral. Although here it's literally integral over some function. Some topological space. Where here it's this map. You get and also the target of this integral, the value of the integral here it lies in the Seymour group, where earlier the integral is a complex number. So, okay, so now I can apply Nekovar's p-adic height. So then now I can consider this integral. So now let's take maybe I should have done this. It's really the dual. So this way, or maybe I do the other way. I take dual here. So maybe I should, let's switch, just change the notation. See, this way actually make it look more like the formulation we had for the Ichino and Ikeda formulation. So now I can consider this integral. Again, this is the class in the Seymour group. Then I put the p-adic height parent. So this is in the dual, the Seymour group attached to the dual Galar representation. So now I can make the following conjecture. So this is one p-adic version of arithmetic GGP conjecture. So you take any you take any phi belong to pi finite part. If I do inside pi of dual, where pi is one of the representations showing up in this cohomology. Again, also assume tempered cos below. So this should be equal to the p-adic L function attached to pi. And take a derivative. Then I have the local term. Okay, so a few remarks. Okay, I have to really impose something. So here, let me just for safety assume p is ordinary. So pi v for all p-adic places. Pi v is ordinary. Let's say for some chosen unitary group, subgroup. Again, this is just because I mean, anyway, here there's also embedded conjecture about the p-adic L function. So the p-adic L function so it's part of the conjecture. So there's a p-adic L function attached to the Rankin-Silberg convolution. So you take the base change of unitary group to GLN. So you do the Rankin-Silberg convolution. And then you take the derivative along the cyclotomic direction. So that's one remark about the p-adic L function. So this might already, in some sense, there's embedded conjecture in this conjecture. Secondly, regarding the local term, so here those local terms. So there's a local term. It's the same as before. So I think that's one reason this looks very I mean, this formulation looks very parallel to this one. Is I'm really literally using the same definition as Ichino Ikeda here, which is I wrote here. So it's purely representation theoretical. It does not involve anything new. It's old local terms used in formulating Ichino Ikeda conjecture. So really, the new thing is you have a integral here. I mean, as I mentioned, its value is in the same or group. Then you take the p-adic height, and you replace the central value of L function by the p-adic L function, the derivative of the p-adic L function. So hopefully, this the formulation is parallel. It's clear how they compare with each other. Okay, so that's the conjecture. So let me just in the last 8 minutes, let me state a theorem. So the result. So I mentioned, in the case of n equal to 2, this is really not much. Not much different from the classical Shimura curve case. So it's kind of known. So what about hard case? So this is still work in progress with Daniel Dizini. So where we we can prove this. So in progress, so we can prove the conjecture. Under a lot of conditions, such as suppose if. So let me. So one. Okay, let me just be sure I didn't miss any important conditions here. Right. Okay. So P needs to be good ordinary. Actually, yeah, not just ordinary, but also good. So the pi. All the p-adic places, so the following conditions. One, so P is good ordinary. So meaning all the places above P, the local representation pi V are unramified. Plus, the ordinary condition, the Hida's operator acts by a p-adic unit. And also all the places above P are split in this quadratic extension. So this means all the places above, all the p-adic places are split. So we can only treat the split case. So secondly, So I have a lot of condition. Well, I mean the key conditions for the representation pi. So let's see pi. So the ramification. So pi v should be either unramified, which is true for almost all places. For the remaining finitely many places, pi v should be of maximal parahoric special. I mean, okay, maximal parahoric. So maximum parahoric level. So pi v at all places, all inert places. So for split place, you can okay, I will ignore. So there's some disjointness of ramification. So they shouldn't be simultaneously ramified for the two factor of unitary group. But anyway, let me just ignore it. So if you like, we can talk later. So the key is for the inert place. So I can only allow maximal parahoric level of the following form. So okay, locally, so WV. So this means pi v has a non-trivial fixed vector by a certain parahoric subgroup defined by a lattice. So this is lattice, which is integral, and so lattice of type, let's call it type T, in the sense of sorry, it's a vertex lattice. So vertex in the sense of Brihat-Tist theory. So in other words, it's a vertex in the building of a unitary group. So concretely, this means this lattice, if you consider its Hermitian dual, so the dual lattice should contain lambda v. Well, that just means lambda v, this lattice has integral value with respect to the Hermitian form. But the condition is that this should be the dual lattice should be squeezed between 1 over the uniformizer. It's called pi v. So this is local uniformizer. So the type T is the length here. T is the length. T is the dimension of this quotient of the dual lattice by the lattice itself. So the vertex lattice just refer to this condition. So refer to this condition that has to be in between the lattice and its translation by uniformizer, 1 over uniformizer. So so the stabilizer Kv will be the stabilizer of this lattice. This is a special parahoric subgroup. So we require such so I require pi v to have such a vector fixed by this maximal compact. So that's essentially maybe the sort of important condition. So so yeah, I mean, so implicitly I want to all the places to be unramified. So this is unramified everywhere, which is a very unfortunate condition in the sense that it rules out rational numbers and quadratic extension over Q, because I mean there's always ramification. So okay, so I have like 2 minutes to describe how those conditions arises when, and you know the key is the key to the proof. So I mean the proof is of course is to compare the Hyperion with the Zagier trace formula. So compare the p-adic height. So if I take so the very quick overview proof or ingredients in the proof is so we compare, it's called intersection p-adic. So this is the p-adic height of the cycle and its translation by the Hecke correspondence. So F is Hecke operator attached to I mean F is a function on G over finite ideals. So K by K invariant for some compact open subgroup K. So I put this p-adic height parent. So I can compare this with the Zagier or maybe a p-adic limit. So a p-adic limit of Zagier-Rayleigh. So a relative trace formula. So Zagier-Rayleigh has a relative trace formula approach. So where now you have to. So I'm going to see what is sort of the new and what is the p-adic limit. I mean, it's a limit, so of a sequence of test function. So you're going to choose. So the Zagier-Rayleigh is a let's call it f prime. It's a trace formula attached to functions on some Hecke operators on GON. So G prime is the base change of G. So G base change to f prime. So it's essentially GON times GON plus GON minus 1 over quadratic extension. So here, what is the limit is about is, okay, you have to fix Archimedean place. So away from P, so at P. So the limit means I'm going to take a family of test function where, so we're at P, so this additional parameter M. This indicates, okay, it's not exactly true, but morally speaking, this will be a application of some standard test function composed with high power of UP operator. So this is essentially, let's say, UP operator to the, say, M power. Well, okay, this it's slightly more complicated, but essentially some power, maybe factorial. Okay, sorry, actually, it's I mean, yeah, it's essentially some high power of UP operator, but you have to also modify a sort of a way to p-adically interpolate. So on the way of the proof, we're using this RTF of Zagier-Rayleigh to prove that exists a p-adic function. So this p-adic function exists under those conditions, and we get a just purely using the relative trace formula, we get a p-adic function from the geometric side of the trace formula. Namely, we p-adic interpolate the orbit integral, which give rise to measures if we have this good ordinary condition. And then the height pair side, we also decompose the p-adic height into local heights, and then we can make use of results on the p-adic version. I mean, on the arithmetic fundamental lemma, computing the local intersecting number relating to derivative of orbit integral and so on. So away from P. So above places for places above P, the local heights we argue like parallel and Dizini's earlier work that under this sort of limit, the local height at P converges to 0. And on the analytic side, we also argue the orbit integral also has no contribution above P if P is split. So that's where the split condition appears. It's basically to eliminate the contribution above all the places above P. So okay, that's a very oversimplifying sketch of the proof, but hopefully I give you the flavor of the proof. I'm running over time already, so let me stop here.
Thanks for the wonderful talk. Any questions, comments, remarks? Yeah.
Hi. Yeah. So in the theorem, like when you prove the formula, you have the construction of the p-adic function.
So the p-adic function is constructed along the proof by using the Zagier-Rayleigh trace formula. So after the conjecture here, yeah, I mean, okay, it depends how general you like. So in the case we have, I think we construct p-adic function pretty generally. I mean, at least for the so for the construction of p-adic function, we only need the first condition. I mean, it's just the split condition. Well, actually not even split. So basically some even more general than this condition. We don't have to impose those conditions because it's purely about Jacobi-Rayleigh's or relative trace formula. So those two conditions later on, they exist because we have to compare with the Heidegger and so on. So on the way of proving this result, we also construct the p-adic. I mean, okay, but we only construct p-adic function maybe in one direction in the sort of this, we only interpolate L value traced by finite order character.
So, I mean, do you have some sort of vanishing also with the condition, like when you are considering LP prime? I mean,
vanishing in you mean can we prove the L function the p-adic function actually is not identical to 0 or?
yeah, like I mean.
No, we cannot. That's not a part of the. Well, you mean for any given pi? No, we cannot prove it here. What we prove is we have some identity, right? So I mean the p-adic is given by some p-adic interpolation of orbital integral. Okay, but it's some it could be cancellation in the sum of orbital integrals, which we cannot predict for any given pi. What we get is is not identical to 0 then. Of course, I think it should be possible to prove, for some pi this is non-vanishing because I think at least some orbital integrals will be non-zero. So to answer your question, if you give me a pi and ask me, can you prove the p-adic function we construct is non-zero? It's not identical to 0. The answer is no. I don't know how to prove it. But on the other hand, this sort of conjecture, this identity we prove tells you that if the p-adic height doesn't vanish, then the p-adic function doesn't vanish. The derivative doesn't vanish. In particular, the p-adic function should non-vanishing, right? But other than that, I cannot predict anything. But maybe that actually reminds me of I forgot to just state one application. So one consequence of this conjecture would be you get some application to the p-adic version of Bloch-Kato conjecture, as formulated by Perrin-Real, and maybe also in conjunction with the work of Fontaine, where if you assume, the order of vanishing of p-adic function should be the same as the Seymour group. Well, at least in this case, I have a good ordinary condition. So there's a canonical choice of splitting in the p-adic height. So really, so we do get a application saying that if you assume the L function has order 1, has vanished order 1 along the cyclotomic direction, then the Seymour group, Bloch-Kato Seymour group, is at least 1, because that means this class is non-zero in the Seymour group. But then you combine with either the work of maybe Yifeng Liu maybe has talked about our joint work on the Benhenson Block conjecture in the rank 0 case. So here there we also prove rank 1 some Euler system type argument which can give upper bound. So in the end you actually combine, or you can use Jetref, Skinner, and Wekovan's ongoing work. Either way, you will give you a upper bound, Kolyvagin type result. So in the end, you get, if you assume that p-adic function has order 1, then the Seymour group has rank exactly 1, at least under these conditions. So okay, in that application, of course, you are assuming that L function has order 1. Implicitly, you are assuming L function p-adic function is non-zero. So, yeah, but back to your question. So yeah, I think it's a hard question, but here we're kind of not touching that question.
Thank you. Yeah.
Any more questions?
Hello. Hi. So, on the left-hand side, the height pairing you have defined. So, does it has any relation with the height pairing defined by Amnon-Besar?
Defined by by
Or
sorry, I didn't hear the height.
integral expression can you have, or some integration like Besar and Vygotsky has defined, right?
Yes, they did it for the curve case, right? Yeah, I think I think Besser might have proved it's the same, right? It's Wekovan's definition coincides with the Besser and Vygotsky, and earlier Coleman and Gross, or maybe even before that, like Tate, they also consider p-adic height for abelian variety. So I think those are, in the case of curve, Wekovan's, so the one I'm talking about is the same as that one. But meanwhile, there's also some other parent of a Besser, generalizing Coleman integral, but that's a different one. That's a different one. So this is the same as the p-adic height for curve defined by by many years ago for curve.
Any more questions? If not, let's thank Professor Zhang for the wonderful talk. Thank you very much, Professor.
Thank you. Thank you.